Modern operating systems juggle thousands of concurrent tasks, but they share a single vulnerability: multiple processes competing for a strictly finite pool of physical resources. Memory, CPU cycles, and disk drives are limited. This competition becomes dangerous because of three strict hardware rules. First, many resources are mutually exclusive. Only one process can write to a specific memory block at a time. Second, the operating system cannot preemptively rip a resource away from a process that is currently using it. And third, processes are allowed to hold the resources they already have while waiting for more. When these constraints align into a circular dependency, the system breaks. Process 1 holds resource 1 and requests resource 2. Process 2 holds resource 2 and requests resource 1. Neither can move forward, and neither will yield. This unrecoverable state is a deadlock. A simple guess is not enough to prevent this. To keep the system running, the operating system must mathematically predict the future, analyzing the entire state space before it grants a single resource request. This brings us to deadlock avoidance, modeled by the banker's algorithm. The operating system acts as a strict financial institution. It treats system resources like cash, and it will only grant a loan to a process if it can guarantee a safe return on that investment. The operating system evaluates the board to determine if the current allocation constitutes a safe state. A state is mathematically safe if and only if there is at least one specific sequence where all currently active processes can run to completion, using only the resources available right now. If the algorithm cannot prove that a safe sequence exists, it denies the request. The process is forced to wait in the queue. The system survives by refusing to enter a mathematically unsafe allocation. This exam snapshot captures a static system state, 5 processes competing for 3 resource types. We see what each currently holds in the allocation column and what remains in the available pool. The max matrix defines the absolute peak demand each requires before it terminates. To determine system safety, the algorithm calculates potential need by subtracting allocation from max. For P0, a max of 753 minus an allocation of 010 leaves a need of 743. It rapidly runs this subtraction down the line to populate the entire matrix. This new need matrix outlines the absolute worst-case scenario. It charts the maximum resources these processes could suddenly demand simultaneously, which the operating system must prove it can survive. We establish a work vector of 3, 3, 2, and a finish checklist for 5 processes. Evaluating P0, its need of 743 exceeds the work pool. The math fails, so it's marked unsafe to execute. The algorithm drops to P1. Its need of 122 fits cleanly inside the available work pool. Here is the core mechanism. The OS simulates completion instead of executing. It assumes if P1 gets what it needs, it finishes and returns its allocated resources. P1 gives back its allocation of 330, expanding our work pool to 532. P1 is successfully resolved. By mathematically reclaiming resources in a simulation, the operating system builds a theoretical buffer. This proves that satisfying smaller requirements first can accumulate the pool needed to handle larger processes later. The algorithm iterates this logic through the rest of the queue. P2 has a need of 600, which exceeds our 532 pool, so it waits. But P3 fits. It simulates completion and returns its resources. Then P4 fits, finishing and returning even more. With the bottom of the queue resolved, the algorithm loops back to the top to reevaluate P0 and P2. The simulated work pool has now swelled large enough to safely cover P0's massive need of 743, and then finally P2. All 5 boxes are checked. The OS has mathematically proven a safe sequence: P1, P3, P4, P2, and P0. But a static state is just a baseline. Processes often interrupt with new demands. Look at Part C of the exam. P1 suddenly requests 1 more instance of resource A and 2 of resource C. The operating system intercepts this request. It temporarily deducts those resources from the available pool and adds them directly to P1's allocation profile. Before the hardware actually changes hands, the OS triggers a completely new iteration of the banker's algorithm based on this hypothetical new state. checking to ensure a safe sequence still exists. Operating systems run these checks dynamically, simulating thousands of hypotheticals every second to catch and deny dangerous requests before any hardware is actually handed over. Because a single safe sequence was found, deadlock is strictly impossible from that initial state. But algorithmic certainty demands computational overhead. Constantly predicting the future places a massive, relentless physical strain on the processing hardware. This chart shows the algorithm's time complexity of O of m times n squared. Executing this matrix operation for every single resource request across thousands of active threads is physically prohibitive in modern architectures. There is also the practical limitation of the max matrix. Dynamic modern software rarely knows its absolute maximum resource requirements the moment it launches. Modern systems often sacrifice pure avoidance for speed by using heuristics and recovery. Yet the banker's algorithm remains the theoretical standard for coordinating resource allocation in concurrent software design.